Hi, and welcome back once again. This is the week 2 video number 2, so we're still behind, but I think we'll be catching up. Hopefully I'll crank out more videos over the weekend. But today's video, we are going to dive into learning more about the encoding of data, and specifically binary, hexadecimal. We'll look at octal as well, how that relates to normal integers, just to help start making more sense out of what we've been looking at. So we left off last time. Oops, got the wrong one up. There we go. Looking in a hex editor called Bless, we were looking at our executable file that we created from an assembly language program. And I think I probably said this, but every executable file you create, if it's something that compiles into machine language like the C programming language or assembly, it's going to generate an executable file something like this, at least if you're doing it on a Linux system. And it's not too terribly different on a Windows-based system. Of course, it's going to have a different file format for its executables and so forth, but so one cannot run on the other and vice versa. But when it comes to text files, let's see, do I still have the text file open here? Is that Bless? Nope, that's not Bless Editor. Well, let me just go ahead and open the text file. Let's see if I can find it. There we go. Some stuff. All right, so now I have two tabs here in the Bless Editor. So looking at a text file, the binary or hexadecimal encoding is much more straightforward because there we're using a thing called the ASCII code. So each of these numbers here is specifically representing a text symbol here. And so that's pretty straightforward. There is some stuff to know about special codes like the new line character and so forth, but that's not that tough to understand. And of course over here we saw that things got a little bit more complicated. We have sometimes the binary code here represents an instruction, sometimes it represents a specific number, piece of data, numeric piece of data. But even when we say grab 4 bytes and want to look at that as a number, there's many different ways of looking at those same 4 bytes. We could look at it as a signed integer, an unsigned integer, and in this case the two happen to be the same. We could also look at it as a floating point number, which makes it something completely different. Or it could just be 1/2 of an 8-byte 64-bit floating point number. It could also be part of an 8-byte integer. We don't have that listed down here as one of the options to look at, but you get the idea. And of course, it could also be split into two pieces, each of which is separately a signed or unsigned 16-bit, or we could regard it as 4 1-byte numbers. Of course, if they're only 1 byte at a time, we could regard those 1-byte numbers as ASCII codes for text. So just kind of depends on how you want to look at a piece of data, how you interpret that data. So all of it boils down to ones and zeros, and so how we interpret those ones and zeros depends entirely on context and what interpretation we want to place on those. The same sequence of ones and zeros can be a number, it can be part of a number, it can be part of a floating point number, etc. So we don't really want to work with ones and zeros because there's just too many of them, and even just looking at these 4 bytes right here that I have highlighted, to the human eye, it's just too much to take in and just at a glance say, oh, that's a well, let's see, what is the first one here? That's you couldn't even translate into that into hex very quickly. So where are we? We're right here. So that's actually a hexadecimal. Let me make sure I'm where I think I am. Let's just grab these 4 bytes right here. There we go. So those 4 bytes, and again, I don't know why it's highlighting these soft highlights. Maybe it's because the first byte I highlighted here was a 00, so it's highlighting all the other 00s. So try to ignore that. It's a quirk of the Bless editor. The dark highlighting is what we're interested in. So at any rate, so where's the first byte is this. even at a glance, realizing that that's BA in hex is hard enough. Maybe if we come and highlight the letters here in what's down. So again, looking at that and seeing that it's a 57 as hexadecimal, or an 87 in decimal, or a 127 in octal. Interesting. Kind of a coincidence that those had the same last digit. Doesn't always work out that way, as you can see from the other examples. Or is that a ASCII W? I mean, what is it? It's easier to look at things like the hexadecimal numbers or decimal numbers, or even octal numbers are a little bit easier to wrap your head around. But octal numbers, I think, are kind of going out of fashion, but they still come up often enough that you should know what they are. So what we're doing today is diving into making sure you understand a little bit of the math behind these different number systems and what's going on. So we're going to start with decimal, binary, hexadecimal, and octal. So let's jump into the notes here. Whoops. There we go. Here's the notes. And yeah, let's take a look at this subpage that I've added, and let's just talk about specifically what we mean by decimal, binary, octal, and hexadecimal. Each of these is a number system or a numeric base. Decimal is just what you're always used to. What you've grown up learning is base 10. It's probably where we use base 10 probably because we have 10 fingers, and humans originally started counting things on their fingers. There are a variety of reasons why ancient civilizations had a lot of things based around 12 that didn't have anything to do with numbers of fingers, but what ultimately came down to us was a system that was base 10. And with base 10, what that tells us is that we have 10 unique numerals. All right, I said digits here, but I should really say numerals. Okay, numerals are used for digits, but the digits are what we use numerals for, but numerals are the symbols themselves. So let me change my notes here to say numerals, because that's much more correct to say it that way. So numerals. Okay, so in the base 10 system, we have the numerals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I think that looks better if I make it Courier, so I'm going to do that. And then the binary system, bi meaning 2, Latin for 2. Binary system refers to a base 2 system, which means we only have 2 numerals to work with. So basically, each digit in a binary system can only be a 1 or a 0. Now, that's probably something you've already heard, but now maybe it's clarified a little bit more why and why it's called binary. Then we have hexadecimal. I'm going to get to octal in a moment. Then we have hexadecimal, which is base 16. Now, you might say, well, that's just, why grab base 16 out of the air? Well, it does have a nice correspondence to binary, and since everything we do in computers is binary, hexadecimal makes a good shorthand for binary numbers, which we'll clarify that in a moment. But let me go ahead and change the font on these to be Courier, so they're nice and evenly spaced. So with hexadecimal, we just reuse the same 9 numerals from decimal, and then we use A, B, C, D, E, F for the next 6 numbers. And those just represent 10, 11, 12, 13, 14, and 15. So A through F represents 10 through 15. And I'm just going to hold off on talking about base 8 until we've looked a little deeper. So let's just talk about decimal, the numbers that you're used to working with and counting in. And let's come down to this table I have here, and let's just think about it's probably not something you've ever thought about much since you were like 8 years old or younger, is just simple counting. So here we have in decimal, we start out with 0, then we go 1, and I'm keeping the leading zeros here because in a computer's memory, every digit of every byte of memory always exists and is always either a 0 or a 1. So I kind of want to have the same kind of idea when we're looking at decimal, hexadecimal, and so forth. So here, leading zeros don't affect anything. 0, 0, 0 is just the same as 0, okay? And then 0, 0, 1, that's just 1. All right, 0, 0, 2, that's just 2. But pay attention to the counting. So we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Simple enough. Then we've run out of numerals, and that's why we have to go to 2 digits. That's why we have to use the second digit. So the second digit goes up to 1 to represent 10, and then we add 0 to that, so 10 plus 0 is 10. So counting up, that makes sense. Okay, we go from 0 to 9, then we go to 10, and now we need 2 digits. But now we can just cycle the first digit again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then finally the second digit ticks up, and the first digit rolls over to 0. So you can kind of think, and another way to think about it is maybe on a speedometer where you see all the digits. As your miles tick up and you see 9999, then you tick up one more mile, all those 9s roll over to 0, and the next digit over ticks up by 1. So, that's just how normal counting works. I went ahead and so like here, when you get up, we go 98, 99. So then both 9s roll over to 0, and then the hundreds digit kicks up by 1, right? So we have the same thing going on regardless of which base you're counting in. We just have different numbers of symbols. So just by thinking in terms of counting, you can understand how to switch from one base to the other. Now, there are faster ways than counting to go from one base to the other, but in terms of understanding what's going on, counting is a pretty good way to do it. So again, in binary, we start with 0, 0, 0, 0, 0, 0, 0. That's just 0. And then we take that first digit, we tick it up to 1, so that's a 1. So binary 1 and decimal 1 look very similar. And you'll notice actually hexadecimal 1 and even the octal 1 over here looks very similar. I guess I will say octal. Okay, so octal, oct, 8. Octopus, 8 arms. Latin for 8. Or maybe it's Greek for 8. Maybe it's both, Latin and Greek. I don't remember offhand. But at any rate, octal means base 8, so we have 8 symbols, 0, 1, 2, 3, 4, 5, 6, and 7. We don't get the 8 and the 9, all right? So, so we're counting up in binary. We count 0, then we count 1. Now we're already out of numerals, so we have to go to the next column, to the next digit, and tick that one up while rolling over the digit that always counts, the ones digit. So notice that this digit just goes 0, 1, 0, 1, 0, 1, 0, 1 as we count up. Just like in decimal, we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, back to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in binary, 1 kind of acts like the numeral 9, because that's the where you are when you roll back over to a 0, right? So 1, 0 in binary looks like a 10, but it's just a 2, which is another tip-off, because whatever base you're in, 1, 0 in that base is the base. So in base 10, 1, 0 is 10. In base 2, 1, 0 is 2. In base 16, if we come across to this line, in base 16, a 1, 0 is 16. So you can see, hopefully that pattern makes sense. And then if we look at base 8, 1, 0 is the same as 8. Okay? So that's another way to think about different bases. Whatever 1, 0 is in that base, that is the base. So if we keep counting up in base 2, we get 1, 1. Then the 1, 1 has to roll over. Just like 99 had to roll over and get 100, 1, 1 has to roll over and get 1, 0, 0 in base 2. That's just 4. Okay? Now 4 is 2 squared, just like 100 is 10 squared. So imagine in base 16, 1, 0, 0 in base 16 is going to be 16 squared. I don't have that in this table, but maybe I should throw it in there just for grins. Down at the bottom here. So you can kind of see the pattern of how you count up in binary. So once you roll over to 1, 0, 0, then you go to 1, 0, 1. Then that first one has to roll over, so the 2's position has to tick up. And so we have 1, 0, 1, 1, 0. And then 1, 1, 1. Now we have all 1s. That's like 999. You add 1. Those 9s have to roll over to 0 to get 1,000. Well, in binary, those 1s have to roll over to get you 8. because 1000 looks like 1,000, but in binary that's just 8. All right. So obviously you need a lot more binary digits to represent the same thing in binary that you do in decimal. Basically, you need about 3 times as many digits, a little bit more than 3 times as many digits to represent the same stuff. So by the time we are here at 255, we need 8 binary digits to represent that at 11111111. Okay? So now let's look at hexadecimal and why hexadecimal is so popular whenever working with computers and among computer scientists and programmers and so forth. And that is because of the connection between hexadecimal digits and binary digits. So let's look at the hexadecimal counting up to 16. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay, and remember A is just 10 in decimal, F is 15. So now that F, that's our last numeral in hexadecimal, so that has to roll over to 0, and the next digit becomes 1, and that is 16. Now look what happened over here in binary. The F was 1111. That rolls over to 0000 at the same time as F rolls over to 0 here. And then we have a 1 here in the next base 16 digit, and we have binary 1 here as well. So what we see is that exactly 4 binary digits are an exact match for 1 hexadecimal digit. So you can always go directly between. So if you just memorize these rows of these 2 columns, let's see if it'll let me. If you just memorize the connection here, and really you only need to count, you don't really even need to memorize. But if you remember the connection between these 2 columns, then you know how each hexadecimal digit compares or converts to a binary and vice versa. Okay. Now there is a similar connection to octal. For octal, you will find that each octal digit goes up, matches exactly 3 binary digits. So if we look here, when the binary is 111, octal is at 7. So that 7 is ready to roll over to 0 and tick the next column up by 1. And when these 111, when those are ready to roll over to 3 zeros, then we kick up by 1 here. And then the same thing happens with the next 3 binary digits. If we come here, for example, there is a 7. Well, actually, we're not going to... I think I am going to insert one more row just so we can see these things roll over. So let me table insert below. All right, so these things are going to roll over. The base 16 is going to be 1FF. I'm adding spaces here. You don't have to add spaces. I'm adding spaces just for a little, to break these things up a little bit. But that's just 1FF. Okay, or not, I'm sorry, that's not 1FF, it's 100. Okay, so maybe you could leave out the space. That depends on what you want to do. I think maybe I will leave it out. Maybe that'll confuse people if I keep it in. But in octal here, the 77, that's like a 99 in normal decimal numbers. So those are about to roll over. So those are going to go to 0 while the next digit goes up by 1. So there's octal. And that's just 256 here. And in binary, actually, and here I am going to break up the digits because it's hard to keep track of them if they're not broken up a little bit. There we go. And then I think I'm going to right justify my binary, because that'll line things up better. There we go. All right, that way all the digits are lined up correctly. Okay, so all these ones rolled over to zeros for 256. Yeah, so that way you see, okay, this digit here of octal, it's ready to roll over, and then the next one kicks up. So once again, when you have the next 3 digits of binary, these 3 digits here, those correspond to this 7, and these 3 digits here correspond to this 7. Now, the reason octal, I think, is tending to be less and less used is specifically because the computing industry has settled on the 8-bit byte as the standard size chunk of data. And because octal uses 3 binary digits per octal digit, it doesn't divide evenly into 8 bits, 8 binary digits. If 9 bits, if the computing industry had settled on to 9-bit bytes as kind of the standard, then maybe we would never bother with hexadecimal and we would only be using octal. But hexadecimal just matches up so much more nicely, byte for byte. Just each hexadecimal digit is half of a byte, so that's just beautiful. But you will see a lot of software, a lot of things will still show you things in octal and use octal, so you should know what octal is and be able to interpret octal as well as hexadecimal. So that is decimal, binary, hexadecimal, and octal, kind of in a nutshell, at least from the point of view of counting. So now there's the next way to think about these numbers, which is interpreting each digit as a power of the base. So we interpret each digit of a number as a power of the base. And I think I'm going to pop this into outline form and specifically take that digit times that power of the base. And then you just add those together to get their number. So in just normal decimal, which hopefully you already know this, and that this is not anything new to you. So in decimal, we have things like, I don't know, 3,296, okay? What does that equal to? Well, that's 3 times 10 cubed, okay? Some of you are probably familiar with the caret notation. It's too much of a pain to keep coming up here and clicking the superscript, and there's not a hotkey for it that I'm aware of. So actually, maybe there is. Let's try Control+. Ooh, that was almost it. Yes, there is a hotkey. Okay, that worked. So 3 times 10 cubed. All right. Plus 2 times 10 squared, right? Plus, that would be 9 times 10 to the first power, right? And plus 6 times 1 or times 10 to the 0 power. To the 0 power, okay? And just to kind of further clarify that, whoops. So that is, it's wanting to like do these calculations for me and it's doing them wrong. OneNote is strange sometimes. So that's just 3,000 plus 200 plus 90 plus 6, okay? So that's the way decimal numbers work for as many digits as you want to work with, right? Now in binary, it's the same thing except you're working with powers of 2. So if I have 11011101, let's say, then what does that equal to? Well, that's going to be 1 times 2 to the power of, let's see, 0, 1, 2, 3, 4, 5, 6, to the power of 6. All right, and I think I can make this go faster then if I do this now. Hopefully I got enough there. So now I just have to change all the powers. 4, 3, nope, not quite enough of them. 1, and one more of these, so and 0. All right, and so we have 1, 1, 0, 1, 1, 0. So I need to make this a 0 times 10 to the 4th, and I need to make this one a 0. I'm sorry, not 10 to the 4th, to the 4th. Remember, in binary, 1, 0 is 2. Okay, so so I'm writing the entire thing in binary. All right, this entire sum in binary. Now, let's see. So if we want to reinterpret the above in decimal, then what do we have? We have 1 times 2 to the 6th. Well, what is 2 to the 6th power? That's 64. So that's 2 to the 6th plus, so now let me do the same thing here. Whoops. Fix the powers, so that's 2 to the 0. 1, 2, 3, 4, and 5. Okay, and then we need to just change our digits. So there's a 0 for that one and a 0 for that one, right? And so what does all that equal? Well, that's just then 64 plus 32 plus a 0 for the 16 plus 8 plus 4 plus 0 plus 1. And so what does that end up equaling? Actually, I think this time it got the answer right for us. So let's just leave it at that. Actually, but I want to drop it to the next line. There. All right, so we're reinterpreting this sum in decimal, but see, whatever base you're in, each digit is just that digit times that power of the base, and the furthest right digit, of course, is always the 0 power, which is just 1, and the second digit is always the base itself, which is that base to the first power. The third digit is always the base squared, so like 100 is 10 squared. Well, in base 2, 4 is 10 squared, so that's why the third digit over adds in a 4. In base 2, 8 is 2 cubed, like 1,000 is 10 cubed. So 8 works like 1,000 in binary, and so forth. So that's how binary works. And of course, hexadecimal then works the same way. If we want to look at larger integers than just 2-digit integers. So if you had, I don't know, let's say 1F3 as your hexadecimal number, then that's going to be equal to 1 times 16 to the squared power plus F times 16 to the cubed power plus 3 times 16 to the, oops, I meant first power back here, not cube power. There we go. All right, so we go 1 times 10 squared, or 1 times 16 squared, f times 16, and 3 times 1. So let's go ahead and say, okay, well, that is equal to, oops. There we go. So interpret the above in decimal. That's just 1 times 16 squared plus 15 times 16 to the first power. Oops. First power, there we go. Plus 3 times 16 to the 0 power, which again equals 256 plus whatever 15 times 16, that's 240, plus 3 times 1 is just 3, which of course equals 499, it looks like. If I did that in my head correctly, that should be 499. All right, so that gives you the way to kind of mathematically interpret what numbers are written in these different bases. I'm not going to bother with the octal example. I think this is enough for you to get how it works. So if you have something in one of these bases, you can convert to the other base, convert to decimal, convert to a different base, that sort of thing. There is, if you want to go from decimal to the other bases, there is a particular trick. I mean, you can kind of figure it out by trial and error, figure out what each digit should be. But there is a particular nice way to do it, which is a little less intuitive. Some of you may already know the method. And we may actually end up writing an assembly language program to do this conversion for us. That might be an interesting project down the road a little bit. But for now, I want you to just understand the basics of how these numerical bases work and how they relate to each other, so that when you come over here, you just have a better feel for why we're even bothering with hexadecimal, and when we're looking at the binary files and so forth, and what that actually means. So we usually use hexadecimal simply to be a shorthand for the binary, because looking at all those ones and zeros is kind of a pain. So instead of looking at bytes as ones and zeros, we look at them as hexadecimal digits, where we know each hexadecimal digit matches exactly 4 bits out of a byte, and each pair of hexadecimal digits represents 1 byte. And that's why the way it's listing this file for us is in pairs of hexadecimal digits. So each pair of hexadecimal digits represents 1 binary byte. We separate them by spaces so we can see each byte individually very easily. And you know, that makes sense. It doesn't really ever make sense to look at the second half of 1 byte combined with the first half of another byte, because the way memory, the way data is organized on hard disks, the way it's organized physically in computer memories, the 8 bits of a byte always go together. There's no taking part of 1 byte and part of another. Now, when we look at bigger things like, say, a 4-byte integer, then it is possible. We could take these 4 bytes right here, that could be an integer, or we could take these 4 bytes as an integer, or these 4 bytes as an integer. So it could be that, you know, that's an integer and that's a 4-byte integer, or it could be that this is a 2-byte integer and this is a 4-byte integer and this is a 4-byte integer. Okay, and so we can break them, we can break and group bytes up however we want, but you don't split the individual bits of bytes up. So that's why we specifically represent the bytes, each byte here in the hex editor. That's specifically why we look at it as a hexadecimal, 2-digit hexadecimal number. Now, some things that you should sort of just kind of commit to memory and try to never forget. For example, you should just always know that FF in hexadecimal, okay, FF, well, you should always know that F is 1111, okay? And just kind of think of it as you've filled it, think of F as you've filled it all up. F for filled, all right? You've filled up these 4 binary digits with ones when you have an F in the hexadecimal. And so FF for hexadecimal byte is the hexadecimal byte that is all ones. And of course, the hexadecimal byte 00 corresponds to the binary byte of all zeros. Okay? Now, how much you memorize automatically going between the other digits, there's not a lot to memorize there, so you could memorize it, or you could just kind of think of mathematical shortcuts so you can go back and forth. But it should not be foreign to you to figure out, oh, I have these hexadecimal digits. What are the binary digits that go with that? I have these binary digits. What are the hexadecimal digits that go with that? You should be able to go back and forth between those. Now, some other things you should know, also those common conversions to decimal. So you should know that FF is 255. 255 is the largest 1-byte unsigned integer. In fact, let me the table. Let's expand this. Give myself more to work with. So here I'm going to start putting some annotations. Largest 1-byte unsigned integer. Let's say it that way. Okay, so and that's something you should just know. Okay, some other things that you should really take to heart is so I'm just going to have a column for notes there. I think I'm going to throw another column in here. Powers of 2, okay? And, of course, 1 is 2 to the 0, right? Let's go ahead and do this. There we go, 2 to the 0. That looks better. And 2 is 2 to the 1st, right? And 3 is not a power of 2, but 4 is, whoops, 2 to the power of 2, 2 squared. And then 5, 6, 7, then 8 is 2 to the power of 3. And so forth. All right. Then we have to actually get up to 16, 2 to the power of 4. I would definitely know your powers of 2 on up to at least 2 to the 8th. You should know that 2 to the 8th is 256, 1 greater than what you can fit in a byte, all right, in an unsigned byte. So notice that at 2 to the 8th, we have 1 followed by 8 zeros in binary. So your 9th digit in a binary number is the 8th power of 2. And that represents 256. So now here's a question to you. How many different numbers are there that you can represent with 8 bits? how many different things can you represent with 8 bits? Or how many different combinations of 8 bits are there? That's not really a trick question. It should be kind of obvious just from this chart. So, but I'm going to put it out there. Pause and think about it before I just blurt it out. So, how many different numbers or whatever things can be represented by 8 bits? So another way to put that, how many different combinations of 8 bits? And I guess I haven't said it explicitly to this class. If you never knew where the term bit came from, or if for some reason it's new to you presently, let's pop over here. Bit, the word bit comes from binary digit. Okay, so bits are binary digits. That's except when they're not. And we'll talk about the exception to that soon. Looks like I'm running up on 40 minutes here, so I'm going to probably cut this video short and then dive right into the next one where we go into some more details on this. But let's see. So back over here on the number systems. So think about that question. All right, how many different combinations can you get out of 8 bits? And start simple. How many different combinations of 1 bit are there? Well, you can have a 0 or you can have a 1. So there's 2 possibilities with 1 bit. How about 4 bit? Or how about 2 bits? Well, out of 2 bits, you can have 0, 0, 0, 1, 1, 0, and 1, 1. So there's 4 combinations of things from 2 bits. What about 3 bits? Well, I can have those 4 combinations plus a 0 in the first bit, or I can have those same 4 combinations plus a 1 in the first bit there. So I get a total of 8 different combinations. Or you can just think, how many things could I count up to? I start at 0 and I get up to 255. So how many things is that? Well, you got to count the 0 as well, so that's 256 things. So 8 bits gets you 256 different things. All right. So now what about how many different numbers, combinations of 16 bits? That's 2 bytes. How many different combinations of 4 bytes? Okay. Or 32 bits. Here's something that's not a trick question at all. What is the maximum signed integer or I should say maximum unsigned integer you can represent with 4 bytes, all right, and express that in hexadecimal. Now, it's actually easier to get the hexadecimal first, all right, rather than figuring out the decimal version of that number or something. But so what is the maximum unsigned integer you can put into a you can express with 4 bytes or 32 bits? And so now let me go ahead and answer these questions. I'm going to answer these questions now, but I'd like you to pause, think about it, try and make sure that you can understand what the answer, figure out the answers to these for yourself before you unpause and have me say, okay? And for some of you, you know, maybe you already knew this, or it was already pretty obvious, depending on your prior exposure to these ideas and your general math skills and things like that. But, okay, so how many different combinations of 8 bits? We already said that's 256. What about 16 bits? Well, notice that the number of combinations for 8 bits is 256. That's just 2 to the 8th, right? It's going to be the same pattern. So that's going to be 2 to the 16th, which will equal not 216. That's going to be 256 squared, which that's not one that I do off the top of my head every day. It's going to be about, not 8. It's going to be in 30,000 something something. No, 65,000, I'm sorry. Yep. So that is 65,536. And what about the number of combinations of 32 bits? Well, that's just going to be 2 to the 32 power, which is going to equal 2 to the 16th squared. You can just plug that into a Google search, one way to calculate it quickly. But that's, let's see, 4,294,000. I'm just going to cheat and copy paste this. There we go. So that's going to be, oop, what the heck was that? Let's try that again. Okay, it's just wanting to grab extra stuff. What on earth? Somehow I was copying more than I thought I was from the Google calculator page. All right, there we go. So there it is. That's the largest, well, that's the number of combinations of things that you can get in 32 bits. That's going to be kind of an important number. We're representing, these are just decimal numbers. And sometimes it's important to remember, keep in mind which format you're using or which base you're representing your numbers in now, since we have these different bases that we're going to work with. All right. So now let's see. What is the maximum unsigned integer that you can represent with 4 bytes or 32 bits and express that in hexadecimal? So as I mentioned, it's kind of easier to get the hexadecimal than the decimal version of that number, because remember, the maximum number you can put into a set of binary digits is all ones. 1, 1, 1, 1, 1, 1, 1. Just like for like 3 decimal digits, 999. 999 is the biggest 3 decimal digit number. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 is the biggest binary number you can have with those digits. But we know that in hexadecimal, F represents all ones for 4 binary digits at a time. So we know that in hexadecimal, this should just be FF. All right? And here I'm throwing in the spaces just so it's easier to kind of parse that out visually. So that's in hexadecimal, which for short, we usually just say hex. And so in binary, that's 1111, 1111, 1111, 1111, 1111, 1111, 1111. Is that enough? Yep, got enough of them. All right, so that's in binary. And so what is that in decimal? Well, if you catch on to all the patterns, you'd realize that, okay, if we have 32 bits, then 2 to the 32 is in binary is a 1 followed by 32 zeros. Okay, so this number is 1 bigger than the biggest 32-bit binary number. So what we can say here is just subtract 1 from the number that we have here. So that's just going to be that. So now what I want you to do is look up the largest unsigned int. Look up max unsigned int in C programming. And lo and behold, what will we find? Well, let's look it up. Max unsigned int C programming. And we'll probably get a link to something about limits.h, which is where these constants are defined for you. And then if I do a search for uint, I believe that will get us where we want. There we go, uint max. Maximum value for an unsigned int. And there it is. Okay. And you'll notice that the maximum value and minimum value for a signed integer, the absolute value of those is about half of this, which shouldn't be too surprising. But next video, I think we might dig in, or I might wait a while, into how negative numbers are represented in binary data, because it's not quite what you'd expect. I mean, you might guess a simple way to represent them, but there's a way to represent them that is much more efficient for designing circuits to perform calculations, and that's the method that gets used, but it's a little bit less intuitive for human beings to look at. So that's for the next video. Hopefully this has oriented you a bit more in what hexadecimal means, what these different number systems means, even what binary means when we're talking at least about numbers. So let's end this one here. This is 50 minutes, so that's definitely long enough. And then I will be getting the next video out as soon as I can.